And so today we're going to start on page 25, talking about solving systems of linear equations. This can be a little trickier than the other stuff, so it's good we're together for this one. Okay. So everything we do in this chapter, this linear programming chapter, it's going to culminate at this big idea at the end for linear programming. So it might seem like we're just doing a bunch of random different things, but I promise you, it's all going to be useful once we get to the last section. And the problems are kind of extensive. You're going to have to know how to do each of these little things here. But when we're talking about a solution to a system of linear equations, well, first, what's a system of linear equations? You've all seen a system of linear equations in this class. The very first day, I showed you a smart notebook of apples, bananas, and coconuts. Okay, there was 3 or 4 equations there, and you had 3 or 4 unknowns. So that's a system. A system is just going to be 2 or more equations that have 2 or more variables. So generally speaking, you need as many equations as there are variables in order to solve it. And if you get into the upper level math courses, there can be linear systems that have 30, 40 equations, but those are usually done by computers. So we're only going to talk about systems that have 2 equations. So let me type out these steps. So first, a system of equations is just 2 or more equations. And let me know, last class they said that there was kind of a delay here, because I guess it might have been because of the internet service. So if I start cutting out, just stop me and I'll slow down. But I know there was some issues last class. All right. The solution to a system is the coordinate, come on now, or coordinates that satisfy all the equations in the system. It's the coordinate or coordinates that satisfy all the equations in the system. All right. So there's 3 possibilities that we're going to deal with in this class. The first one is called a unique solution. That means there's only one coordinate that satisfies both equations. And that's the standard here's your linear, here's your lines, coordinate plane. First line will do blue. Second line will do red. So I just have these 2 lines, 2 equations. I graph them to make lines. And when I find the solution, it's just going to be this xy value, this coordinate x comma y, that falls on both equations or both lines if I graph them. Okay, that's just a unique solution. So we'll just say one solution in this particular case. Now you can have a system that we call an inconsistent system that has, oh, let me do that in black. No solutions. So in this particular case, there are no solutions. Can anyone think of a way or a situation in which there would be no solutions to a system with 2 equations?
Parallel lines.
Hey, parallel lines. If I'm trying to find the point of intersection and there is no intersection, I can't find the point of intersection. And that happens when the lines are parallel. And that just means they're parallel, those 2 little arrows. And the last possibility is called a dependent system. Darn it, I did it again. Any idea how that can happen, where this would be the situation in which there are infinite solutions? How's that going to happen?
If the lines are the same.
Hey, my man Joe is killing it. Yes. If they're the same line, or you could also say, or if one line is on top of the other line, same line actually makes more sense. So we'll go with that. But you have one line on top of the other line. So every point on the one is on the other. So since they go on forever, you have an infinite number of solutions. So we'll say, we'll go back to my pen, we'll say same line. Now, how do you determine what system you have if you have no solutions or infinite solutions or one solution? When you solve these, remember when we just solved the equations and we ended up getting something funky like 16 equals 25, and we knew that meant that there was no solutions? The same thing's going to happen here. So you get something like 16 equals 5. You're like, oh, these lines must be parallel. There's no solutions. And if you get something like 0 equals 0, you can assume that if they're the same line, so there's an infinite number of solutions. I think we'll see an example of both today. So just like with graphing, okay, I told you before that if the line is written in general form, ax plus by equals c, I would prefer you graph it, or I would graph it by using intercepts, right? If you had something like 3x plus 4y equals 12, I would suggest graphing that using intercepts. And if I said it was written in slope-intercept form, graph it using your y-intercept and then the slope. So this is the same kind of thing. So depending on how the question looks, we're going to use one of two different methods. Okay, you've probably seen them before, but the first one is the substitution method. So we're going to use the substitution method. Write this down. When at least one of the variables, new keyboard, is solved for. So we use substitution method when at least one of the variables is solved for. So notice here, I have y equals this, y equals this. So in this particular case, the y is already solved for. I have a y by itself on one side of the equation. Doesn't matter if it's in both. All you need is just one of the equations to be solved for y or x. And what I'm going to do here is I'm going to substitute the expression that y equals in for y in the other equation. I'm going to substitute the expression that y equals into y in the other equation. So here I see y equals 5x plus 7. But here's a y right here. So I can take what this y equals and substitute it in there. We did this when we were talking about copy machines, depreciating copy machines, and MathCo and CalcCo. You kind of can set them equal to each other. Okay, but I'm replacing this y with its equivalent expression, because if there's two variables in an equation, you can't solve it. So I have to get rid of one of the variables by replacing it with something involving x. So here we have, instead of, I'm going to rewrite the second equation, y equals 2x plus 1. Instead, I'm going to write this, 5x plus 7 equals 2x plus 1. This was a y. I just replaced it with what y equals. So now I have an equation that only involves x, so I can solve it. So you can really move anything you want. I'm going to subtract 2x, I get 5x minus 2x is 3x plus 7 equals 1. I have the 3x's by themselves. Now I can get rid of this. I'm going to subtract 7 from both sides. And I get 3x equals negative 6. Solving for x. Divide both sides by 3, get x equals negative 2. Now, if we were taking this class in person, a lot of people on the exam would stop there. I got the answer, I'm done. Circle it, x equals negative 2. That's only half the solution, because the solution to a system of equations is the coordinate x, y. So I need the y value as well. So I can take this value of x and plug it back into either equation. I know it's going to be the same because that's where they cross. So I'll just take it and plug it back into the easier of the two. So I get y equals 5x, well, 5 times negative 2 plus 7. So I get y equals negative 10 plus 7. So I get y equals negative 3. So if you were to graph these two lines, they would intersect at the point negative 2 comma negative 3. Let me just show you. If it loads. 5x plus 7. And the other one, 2x plus 1. Okay, here's the two equations, and notice that they cross right there. Negative 2, negative 3. So we're good to go. So normally they want you to write it as a coordinate, so you can say, this is negative 2 comma negative 3. There's that stupid E again. I think there's something wrong with my pen. If I click the button, an E pops up. Well, whatever. I'll leave it there, I guess. Okay. There we go. And he's gone. So let's write the steps for this process. So again, use when one of the variables is solved for in either equation. We will replace that variable in the second equation with its equivalent come on, that expression. Then solve for remaining variable. Use the solution for that variable to solve for original substituted variable. It's a little winded, but that's what you need to do. So we're going to use this method when one of the variables is solved for. We will replace that variable in the second equation with its equivalent expression. There will be one variable left, and we'll use the solution for that variable to solve for the original substituted variable. Okay, so looking at example B, I wouldn't personally use substitution here, because notice the x's or y's are not solved for in the first equation, and the x and y is not solved for in the second equation. These are both written in general form, standard form. So just to make things easier for us, I'm just going to solve one of them for one of the variables. So I'm just going to solve this first equation for x. I'm going to get x by itself. So if I subtract y from both sides, I get x equals 3 minus y. I'm just going to cross that up. Okay. So my second equation is y plus x equals 5. but I know x equals 3 minus y. So I can take 3 minus y and substitute it in for x. They don't have an equation that only involves y's. So I'm going to get y plus x, but instead of x, I'm going to write 3 minus y, because that's what x equals. And I get 5. Okay, keep going, keep going. I'm going to combine like terms. I have a y and a negative y. They cross out. I'm left with a 3 equals 5. That doesn't make any sense. Okay. Well, let me pull I forgot to pull the chat up. Oh, let me catch up on these questions. Yeah, it doesn't matter which equation you plug it into first. It does not matter at all. Yeah, you get -3 if you use either one. Very good. Thank you for answering that question from Yadiomi. All right, cool. Yeah, if you can, I would say if you have the time, plug them into both, because then you'll know you're right, because you get the same answer regardless. But as soon as you get something like this, it doesn't make any sense. This is funky, and funky implies no solution. This is an inconsistent system. If you were to graph these lines, they would be parallel. They wouldn't cross. Before we leave, Allison, I'll check. I don't think there's a ton of them. I believe maybe like there's two or three possibly, but I don't think there's too many. But we'll check together before we leave. Okay, so what do we do? I hate no solution. Oh, how many of the no solutions? There's probably like one of them, maybe. I don't know if there's any of them or not, but probably if there is, it's just gonna be one. So what do we do if it's not written in standard form? We have a second method called the addition method. So we're going to use this when both of my equations are written in standard or general form. Notice the x's and y's are on the same side of the equation. Okay. And what we want to do is we want to obtain, we'll write these down at the bottom, these steps, but we want to obtain matching opposite coefficients in front of either variable. Matching opposite coefficients in front of either variable. So we want the same number, but different signs in front of either the x or the y term. All right, so if you'll notice, I already have a +2 and a -2x. So I already have what I want. And why do we want that? Because once you get it, the way to solve is we're going to take these equations and add the equations together. Okay, so I'm just going to take these the way they are written right there. And I'm going to draw a little adding bar and a plus sign. And we're going to add them straight down. Make sure they're lined up and add them straight down. So since I had opposite matching coefficients, the 2x and the -2x cancel out. Now I have -6y plus 4y. If I add those together, I get -2y. I have 8 and -10. If I add them together, I get -2. This seems weird to some people, but you can add equations. If I have an equation x equals 4 and y equals 3, if I add these equations together, I get x plus y equals 7. And that's fine. Nothing wrong with that. So I just have to solve this now because there's only one variable left. Divide by -2. And I get y equals +1. Now, again, you're not done. You want to keep going until you have the entire coordinate, the x and the y value. So I'm going to take this value for y and plug it back into either equation. It doesn't really matter if one looks easier than the other one, just do that. I'll plug it back into the top equation. So I get 2x minus 6 times y, which is 1, equals 8. So I get 2x minus 6 equals 8. So I get 2x, add 6 to both sides equals 14. And so I get, divide by 2, x equals 7. Now, if you had the time, plug that back into the second equation, just see if they match up. On the quiz, will you make you try to find this? On the test, it'll say solve this system using substitution or solve this system using elimination, but I don't know which method you're using anyway, so feel free to use any method you want. There's not a right way to solve it. So even if it says substitution, you can solve it any way you see fit. Okay, but I will tell you which one to use, but you don't have to listen to them. So the solution to this system is 7, 1. Okay, let's write these steps. So step number 1, through multiplication, obtain matching opposite coefficients in front of either variable. After you have that, add the equations, solve for remaining variable. Learn how to type better. Use that solution to solve for original eliminated variable. So through multiplication, we're going to obtain matching opposite coefficients in front of either variable. Doesn't matter which one. Sometimes it's one way more easier than the other. Once we have that, we're going to add the equations together. Then there should only be one variable remaining, which we will solve for. And then we'll use that solution to solve the original variable that we got rid of to begin with. So here we have 4x plus 3y equals -1, and 2x minus y equals -13. So we could get rid of either variable if we want. We can get rid of the x's. If I want to get rid of the x's, notice, watch this. I can multiply the bottom equation by -2. So if I multiply the bottom equation by -2, I'll have a 4x and a -4x. I could also multiply the bottom equation by +3, in which case I'll have a positive and -3y. Doesn't matter, it's a personal preference. So let's just go with the 3. I'm going to distribute this 3 to every single term in that second equation. Sometimes you might have to you might multiply both equations to get some number in common. So I'm going to rewrite the top. The top is just 4x plus 3y equals -1. The bottom equation now is 3 times 2x, which is 6x. 3 times -y, which is -3y. And 3 times -13 is -39. Now we're just going to add the equations together. And we have our plus sign. So I have 4x plus 6x, I get 10x. I have 3y and -3y, they're going to cross out. That's why I did that. And I get -1 plus -39 is -40. Now I'll just solve this for x. Divide both sides by 10. X equals -4. But again, that's not the answer. That's half the answer. You'll know that when you plug in the answer on my match, like there's an empty box here. I have to find the other coordinate. Take that value for x, plug it back into either equation. So I'll do it in the first one. It shouldn't matter though. 4x, so 4 times -4 plus 3y equals -1. So I get 4 times -4 is -16 plus 3y equals -1. Solving for 3y, I'm going to add 16 to both sides. I get 3y is -1 plus 16 is positive 15. Solving for y, divide by 3, we'll get y equals 5. So my solution is -4, comma, 5. Any questions at all? Yes, Allison, what is it? What do you got for me? So I picked 3 because I wanted to get the same number in front of the x's or the y's, so that when I add the numbers, add the equations together, they're going to cross out. So let's just say you want to get rid of the x's first. I could multiply. Yeah, right. It makes it much easier. I could multiply the first equation, I'm sorry, the second equation by -2. So I'll get -4x plus 2y equals positive 26. And then when I add those, the x's will go away. Yeah, you don't have to ever do it this way, but I just think it's easier to do it this way when they're both written with the variables on the same side. Yeah. Okay.
Are you only supposed to do the bottom or the top?
It does. It
On B-
depends. It's totally up to you. So we'll look at ones that you can just pick. We'll talk about when to use which one. We're gonna skip example 3 because it's a really ugly problem. Let us try. So looking at the homework section, let's try 4. Now these first two, it says use the substitution method. I think Joe asked, but I wouldn't use the substitution method for these. I would use the elimination method because they're both written in a standard form. But I'll rewrite one real quick. So looking at number 2, I'm going to rewrite this equation, this bottom one, like this. Y equals -5x plus 24. Now, I don't think these are ugly, but they might be. So take a few minutes, see if you can come up with answers for 2 and 4, and then we'll share out. I'm going to make sure they're not ugly equations, though. Desmos. Now, number 2, you get something pretty. And number 4, sorry, let's see. $34. Yeah, 4 you'll get big numbers, but you'll get they're semi-pretty numbers. They're not decimals or anything like that. Because if you get a large numbers for number 4, you didn't do anything wrong. Anyone get an answer for number 2 they want to share out?
I'm in the middle of it.
Okay. Brianna, that's a good question. So I think I told you guys in my announcement from class on Monday that I was going to push it back. So it is currently, it's currently due the 12th. So we only have, let's see here, we only have systems of linear inequalities and the linear programming. So we really only have 2 sections left for this chapter. So it looks like if you look at the calendar, Friday the 5th, we will do systems of linear inequalities. The 8th and the 10th, we'll do the last chapter, last section, because those problems are long, linear programming. And then, so if you want to turn it in, your spring break is the 15th through the 19th. So if you want to turn it in after Friday the 12th, that's okay too. I'll probably grade these assignments sometime on the 13th or 14th. But if you want to wait longer to do them, just email me when they're done, so I know to go in and update the grade. Okay. But so your official due date is the 12th, but I don't care when you turn them in, just email me sometime over spring break when you do have them complete. So I go in and change your grade.
So just the 12th and nothing changes?
It's the 12th, but if you want a couple extra days, you can have it. So just if you want to do them on Sunday night, the 14th, you should be celebrating Pi Day that day though. But if you want to do the homework on the 14th, just email me when they're done and I'll update your grade.
Okay.
And yada 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 asked me where on the announcements page there is a lecture from 224. The third thing down is a lecture from 224 on solving systems or graphing inequalities. And then under our course materials, under recorded unit 2 lecture videos is the class before that, linear equations review. So there's one under course materials and one underneath the announcements. Besides that, you should all be good to go, caught up. Okay. Any answers for number 2?
Number 2, mine is x equals negative y, no, negative
What's your final answer? I'll share the final answer out, then we'll go over together.
negative 4 and 10.
Do we agree? Okay, so let's try this one together. So I'm going to take what what y equals, which is negative 5x plus 24. I'm going to substitute that in for y right there. So this first equation is going to become 3x plus 4 times y. But y is negative 5x. So you're going to have to use parentheses plus 24. And that's going to give me 28. So now I have an equation with one variable, x. So I can solve it. I'm going to distribute just like we did in the very first section of this chapter. I got 3x. 4 times negative 5x is negative 20x. 4 times 24 is 96. That gives me a total of 28. I can clean up that left side. 3x and negative 20x is negative 17x plus 96 equals 28. Where'd my calculator go? Oh, I need that. There we go. So I want to get the 17x by itself. So I'm going to subtract 96. I get negative 17x equals, this is going to be negative, what is this? It's negative 68. And then solve for x. Divide both sides by 17. Negative 68 divided by 17. It's 4. So x is 4. So now it's a matter of just solving for y. And I already have an equation that y is equal or by itself. Y is isolated here. So I'll just plug in 4 for x. So I get y equals negative 5 times 4 plus 24. Y equals negative 20 plus 4. 24. So y equals positive 4. So my solution to this system is the coordinate 4 for x, 4 for y, 4 comma 4. Okay. Any questions, s'il vous plaît?
Wait, that's what we're supposed to, I thought we were supposed to try to find like negative 4 times 5 and
You
Wait,
could, but since
or-
I changed this problem to be y equals because I wanted us to use the substitution method, you could still do that, but you have to make sure you keep everything on the same side. So you can multiply the bottom equation by -4, and you should have still gotten the same thing. Like we're gonna do, we'll do number 4 that way as well. So number 4, I'll use that technique. I'll use the elimination technique. So I want to get matching opposite coefficients in front of either one of the variables. If I want to get rid of the x's first, you'll notice I have to multiply both equations by something because I can't multiply 3 by something and get 7. So I think it would just be easier to multiply the second equation by 2. So then I'll have negative and positive 4 in front of my y's. So the second equation, I'm going to distribute the 2 to everything because I want to get these matching opposite. Once I do it, it might become clearer. So the first equation is going to stay the same. 7x minus 4y equals 34. Oops, 34. And now since I've multiplied the second equation by 2, I'm going to get negative 6x plus 4y equals 40. So I have a positive and negative 4 in front of my y's. Okay, does that make sense? Got it, Yomi?
Yeah, I got it.
Dan's got it. Okay, cool. So now once you have that, you can add these equations together. So when I do that, I get 7x and negative 6x gives me positive 1x, negative 4. This is elimination, yes. Negative 4y and 4y. Sometimes called the addition method. I don't know which one my math uses, but they're synonymous, elimination or addition. And I get equals 34 plus 40, which is 74. Ugly number, but it is a number nonetheless. So I get x equals 74. So now that's only half the answer. So I have to take that solution and plug it back into either equation for x to find y. Doesn't matter which one you use, just pick the one you think looks easier. I'll do the first one. 7x, go down here. I'll put it over here, 7x. So 7 times 74, because x is 74, minus 4y equals 34. Seven times 74, I got 518 minus 4y equals 34. I'm gonna get the y's by themselves, so I'll subtract 518 from both sides. And I'll get negative 4y equals 34 minus 518, negative 484. And then divide by -4, and you get y equals 121. So the solution to this system is going to be the coordinate 74, comma 121. Yep, that's fine, Joe. I'll see you on Friday. Are there any questions about any of this? So there's a lot of example questions in the practice problems, systems of linear equations. Don't feel the need to do all them. How many are there? Let's see here.
33.
30, oh yeah, 33 exactly, each worth 1 point. Yeah, that's an awful lot. So just give some of an attempt. Try doing some using substitution. Try doing some using elimination. And there are some that you can use graphing. They have the graph there for you. You can give them a shot as well. And again, we'll start Friday's class with any questions you guys have from any of those practice problems, if you have any questions. So anything else? Anything you want to clear up? Going once, going twice. All right, then I will see you all Friday. Have a wonderful day.